Good morning, everyone. All my AdMath prodigies. I'm back for to do some more work with you. All right, if you look at the heading there, it says further differentiation right there. So we're going a little deeper and doing more stuff with our ability to differentiate. All differentiation and applications so far were centered around the polynomial function. An example is showing up right there. So let me just quickly review how you differentiate a function like that. More so the different notation that you can use to differentiate that. We know the regular, if y is equal to 7x squared minus 3x plus 4, the first derivative, or dy dx, can be written as 14x minus 3. Y'all are definitely experts at that by now. Now, you don't always call your function a y. Sometimes you call your function f of x. So if I'd call it f of x instead, equals 7x squared minus 3x plus 4. Then, I think I introduced this notation before. F prime of x would have been the notation here. And the result is the same, 14x minus 3. The notation I have not introduced as yet, though, is this one. d dx of 7x squared minus 3x plus 4. What that is telling you to do is to differentiate with respect to x, the function 7x squared minus 3x plus 4. And how do you differentiate that function with respect to x? Well, you apply the polynomial rule, and here again the result is the same, 14x minus 3. So here I just want I wanted you to get familiar with the three main ways that you can indicate you're differentiating a function. You can call it a y, and then the notation is dy dx. Or if you call the function f of x, the notation for differentiation will be f prime of x. Or you can just say d dx, which means differentiate with respect to x, the function 7x squared minus 3x plus 4. Slightly different way you can read it sometimes. I use them interchangeably. Sometimes I would say differentiate the function 7x squared minus 3x plus 4 with respect to x. So sometimes you can say it that way. Okay, that takes care of that. And all right, what else do I have in store here for you? Well, I'm going to get into the other rules that you can use to differentiate, but before we do that again, let's again just recap a little bit. Just give me a minute. Let's say I have y is equal to 1 upon root x. Do you remember how you would go about differentiating that? The first thing you would do, you'd rewrite it as y is equal, as y is equal to 1 upon root x, and then you'll throw the root x up into the numerator. Y is equal to, 1 upon root x, 1 upon x to the half. And then you throw the x to the half up into the numerator to get y is equal to x to the minus a half. And now it's definitely in the form of a polynomial, so dy dx gives me what? Minus a half times x. Remember, you take the power and subtract 1. Minus a half minus 1 is minus 3 halves. If I tidy that up, I'll have minus 1 left on top. 2 is already on the bottom, and I'll throw the x to the minus 3 halves down to get x to the positive 3 halves. I can tidy that up even a little bit more. And you finally get dy dx is equal to minus 1 upon 2 times the root of x cubed. I know you all know your indices and things, so I don't have any problem in just writing that down. and know that you know what's going on. Okay, let's do another one. Ooh. Yes, based on the rules that we've established so far, the only thing you probably might want to do with this is expand your brackets and thing. Oh boy. What you doing? What you doing? You would want to expand your brackets, right? So everybody can expand the perfect squared, I think. I know. End up here at y is equal to square the first, 4. 2 times first times the second. 2 is 4 by minus 3, that's minus 12x. And square the second, plus 9x squared. Okay, you don't necessarily have to spin it around to find your dy dx. You can just say dy dx from right here. Dy dx is equal to minus 12 plus 18x. So these methods of differentiation are well known. Okay, I'm on the verge of introducing another rule for differentiation, introducing the chain rule in both the long and the short forms. How about if you had to differentiate y is equal to 2 minus 3x, the same 2 minus 3x, but instead of to the power 2, to the power 9? What are you going to do there? I mean, you can clearly see that it's not convenient to try to expand the brackets. You can take the whole exam in trying to figure out how to expand those brackets. Put 2 minus 3x side by side 9 times? I don't think so. So, because it's inconvenient to expand it, does that mean that it can't be differentiated? And the answer is of course not. You can still differentiate a function like that. You just have to introduce a new rule. And here it is. It's called the chain rule for differentiation. The chain rule. How does that go? I'm going to show you both the long and the short form for the chain rule. Right back the function. Y is equal to 2 minus 3x to the power 9. Like I said, clearly it's not efficient to try to expand your brackets. So what's inside the brackets? That function inside, just the 2 minus 3x. I'm going to call it u. So I'm going to say let u be equal to the 2 minus 3x. And therefore the function becomes y is equal to u to the power 9. That's interesting. Now, if you look at the substitution itself, that is like a function on its own. U is equal to 2 minus 3x. And I can differentiate that. The variables are u and x. So if I were to differentiate that, that would be du dx, wouldn't it? And the result would just be minus 3. The second expression was y is equal to u to the power 9. If I differentiate that, the variables are y and u, so you'll get dy du, and that would be equal to 9 times u to the power 8. The question now becomes, because obviously the original function which related y and x that I wanted to differentiate, effectively I wanted dy dx. At this point I have two expressions, or two derivatives. I have du dx and I have dy du. And the obvious question is there a way I can combine those two? Is there a way I can combine dy du with du dx to get dy dx? And the answer is yes. If I take dy du, multiply it by du dx, look at the du's. What do you think is happening to them? There and there. What's left over? Just what you needed. dy dx. So let me write it down. This is the chain rule. dy dx is equal to dy du times du dx. So let's put them together and see if we can get dy dx. Dy dx is equal to the expression for dy du, which is 9u to the power 8 times du dx, which is 3. Minus 3, sorry. Negative 3. The answer there will be minus 27 times u to the power 8. One more step, and that would be, because the y function was a function of x, I like to rewrite dy dx also in terms of x. At this point, if you notice, dy dx is in terms of u. So you'll plug in back, remove u, and put back the dy and put back the expression in terms of x that represented u. And I'll end up with dy dx is equal to negative 27. The expression for u was 2 minus 3x. So this would be times 2 minus 3x to the power 8. And that is how I can apply the chain rule to get my dy dx. That's not too bad. Now, what is interesting is that's a long form of using the chain rule, this thing right here. And for the most part, you use it when you're doing doing certain applications, like, for example, connected rates of change. You want to multiply one rate of change, dy du, by another rate of change, du dx, to get a third rate of change, dy dx. And so we're going to use this form of the chain rule, this long form of the chain rule, when we're doing applications. If you just wanted to differentiate the function, if you just wanted here's y, find dy dx, and you have to apply the chain rule to do it, there's a short way to do it. Here's the short form of the chain rule. If y is equal to some function of x raised to a power, then dy dx is equal to, you drop the power, n, write back the function, f of x, subtract 1 from the power, n minus 1, and then you multiply it by the derivative of what's inside the bracket. Now, you remember we introduced new notation. If whatever I have inside the brackets is f of x, when I differentiate that, that becomes f prime of x. This is the short form of the chain rule, and this is how you want to use the chain rule. If the only thing you wanted was to differentiate the function. If you were using it in an application, then you probably want to use the long form of the chain rule. So application form or long form. And this is a short form of the chain rule. So let's apply it. Let's see how it's applied. I'll take back the same function I started out with, 2 minus 3x to the power 9. Y is equal to 2 minus 3x raised to the power 9. Well, it certainly looks like there's a function of x inside the bracket, and it's raised to a power. According to the rule, if I just want to go directly to dy dx, I drop the power in front, 9, write back the f of x function inside the brackets, which is the 2 minus 3x. Subtract 1 from the power, 9 minus 1 gives me 8. If this pen will write, that would be nice. Times the derivative of what's inside the brackets. Inside the brackets, I have a simple polynomial, 2 minus 3x. When I differentiate that, I just get negative 3. So one more line to just tidy up my result. Dy dx is equal to 9 by minus 3 minus 27. I have to multiply what's on the outside. I can't multiply anything inside the brackets because it's governed by a power of 8. So 9 by minus 3 is minus 27 on the outside. And then 2 minus 3x to the power of 8. This is definitely the way you want to use the chain rule, until or unless there's some application that you're going to use it for. All right. Let's try another example. And we'll do it, we'll differentiate it both ways again. This is example number 2. One of there was example number 1. Yes, okay. So y is equal to 2 minus the square root of 2 minus 3x, which we'll rewrite as y is equal to 2 minus 3x raised to the power of a half. We're going to do both forms of the chain rule again. We're going to call inside the brackets, we're going to call that u. So we're going to say let u be equal to 2 minus 3x. If we substitute it into that function, we'll get y is equal to u to the power of a half. If we differentiate each one individually, first one gives me du dx is equal to minus 3. The second one gives me dy du is equal to a half times u to the power minus a half. We could tidy this up right now. The dy du is equal to 1 upon 2 u to the half, or 1 upon 2 times the square root of u. Okay. Now we're going to put the two together to get dy dx in the chain rule. Dy dx is equal to dy du times du dx. Dy dx is equal to dy du, that's 1 upon 2 root u times du dx, which is negative 3. This becomes minus 3 upon 2 times the square root of u. One more step, I should not leave my function in terms of u, so I'll plug in back what u was, and I'll finally get dy dx is equal to minus 3 upon 2 times the square root of 2 minus 3x. Voila. It's not so difficult, at least I don't think so. The second way to differentiate that using the chain rule is to, let's see, y is equal to 2 minus 3x. Well, let's start out with the root of 2 minus 3x, which is 2 minus 3x to the half. Clearly, y is written in the form f of x to the n. The chain rule says dy dx is equal to n, drop the power down, which is a half, times function 2 minus 3x. Subtract 1 from the power, half minus 1, that gives me a power of minus a half. And then differentiate what's inside the brackets. What's inside the brackets, the derivative of what's inside the brackets, it's just negative 3, like so. Dy dx is equal to, okay, let's see what's going to stay on top. The only thing that's on top is the negative 3. 2 is already in the denominator, and I can take the 2 minus 3x to the negative a half and throw that down in the denominator. So this becomes 3 on top, 2 is on the bottom, and then the 2 minus 3x comes to join, 2 minus 3x to the half, positive a half joins it. And the other thing I'll do here to tidy this up a little bit more is to write it as dy dx is 3 upon 2 times the root of 2 minus 3x. So my suggestion is as follows. Again, I think I said it before, but I'm going to say it again. If they just give you a function, say here, y is equal to such and such, and you have to use the chain rule, and they just want you to differentiate it, use this second short form of differentiating. The other form is, like I said, is more applicable when you're doing rates of change examples or rates of change applications. Okay, that's all I want to say about the chain rule. Let's go on to the next rule. which is the product rule for differentiation. Product rule for differentiation. And you get the impression that the product rule is applied when you're differentiating the product of two functions. If y is equal to u times v, where both u and v are functions of x, then to get my dy dx, this is how I do it. V times du dx plus u times dv dx. Differentiation does not distribute over multiplication. If y is a product of two things, you don't differentiate each part separately and put, paste them together. You could do that with addition and subtraction. In one of the earlier videos, I would have mentioned that differentiation distributes over addition and subtraction. So if I have a function made up of several parts that are added and subtracted, you can differentiate each part and then add and subtract the results back together to get your result. It doesn't work for multiplication. You can't just differentiate the u, differentiate the v, multiply those two results to get dy dx. That's not the way it works. This is the rule right here that you're going to use to find your dy dx. Now, the first example is a relatively simple example. In this case, you don't have to necessarily use the product rule. If you look at those two brackets, that's easy to multiply out, get a standard polynomial, and then differentiate. But I want to show the use of the product rule. The second one might be a little more tedious if you try to use the product rule there. Sorry, if you try to expand the brackets there. But I'll probably use the expansion as well to show you, compare the two methods. You are already seeing that there's no, as the functions become a little more complex, you're starting to see that there may be more than one way you can use to differentiate your function. So, let me use the product rule. I'll call the first part u. U is equal to 2 minus 3x. I'll call the second part v. V is equal to 1 minus 4x. If you look at the product rule, it requires v, it requires du dx, it requires u, and it requires dv dx. So let's get those parts. If u is equal to 2 minus 3x, then clearly du dx is negative 3. And if v is equal to 1 minus 4x, then dv dx has to be negative 4. And all I have to do to get my dy dx is to put them together in the way the chain rule, the product rule says. Dy dx is v first, so that will be the 1 minus 4x, times the du dx, which is negative 3, plus u, which is the 2 minus 3x, times dv dx, which is the negative 4. And what I'll do here is open up my brackets. Let me open up my brackets here. Dy dx is equal to, multiply the minus 3 into the first bracket. I'll get minus 3 plus 12x. Y'all please double check my algebra. Sometimes I make some silly mistakes. So double check, make sure all these multiplications and opening brackets and so on are okay. And let me know if you find an error. Minus 4 by 2 is, that looks like minus 8. And minus 3 by minus 4, that looks like plus 12. Ooh. Plus 12x there. Dy dx is therefore 12 and 12, that looks like 24. 24x. And minus 3 and minus 8 is minus 11. That's your dy dx. Let's check it using the other method. The other method, remember me, I didn't have to use the product rule in this particular example. I could have just expanded the brackets. So let's see if that works. Check. Let me write back the y is equal to 2 minus 3x times 1 plus 4x. Okay, if I expanded the brackets first, so I still write back y is equal to, that's 2 4 is 8x minus 3x, that's plus 5x. For real? I know I made an error here somewhere. And then minus 3 minus 12x squared. I know there's an error in here, so let me go back and find it. 2 minus 3x. I get minus 3 when I differentiate. 1 plus 4x, man. Like I had a premonition. That was 1 plus 4x. So v was, let me go back and change this, please. This is 1 plus 4x, so this would have been a plus 4. And 2 minus 3x will give me minus 3. So 1 plus 4x. Oh, Lord. I definitely had a premonition, which is why I said double check my stuff. Let's try this again. All right. All right, 2 minus 3x, you differentiate, you get minus 3. 1 plus 4x, you get 4. So dy dx is equal to v du dx plus u dv dx. Dy dx is v 1 plus 4x times du dx, which is negative 3, plus u 2 minus 3x times dv dx, which is a plus 4. Dy dx is therefore minus 3 minus 12x, and this would be plus 8 minus 12x. Finally, tidy that up and you get dy dx is equal to minus 12 and minus 12 is minus 24x, and 8 minus 3 is plus 5. I kind of knew I wasn't going to get the same result when I got to this expansion here. All right, so that is now I know that's for sure. That's the correct answer. Let's go back to the second method, which we're using as a check. 2 minus 3x times 1 plus 4x. Open up your brackets. Double check that again. That's 2. That's 8. 2 4 is 8. Minus 3x is 5x. And minus 3 by 4 is minus 12x squared. And this is your standard polynomial. Dy dx is equal to, this would be differentiated 2, you get 0. So you get 5 there from the 5x and minus 24 x. There. Same result using either method. Now, you wouldn't have a choice necessarily as the functions that you have to differentiate using the product rule become more complex. I just started off with a relatively easy one. All right, let's try the other example. Yes, the next example is y is equal to 2 minus 3x. I don't know what I got with y equal to 2 minus 3x. I've been using it for quite a while. Yes, y is equal to 2 minus 3x times 1 plus 4x all squared. I'll make it even more, slightly more complex. I'll make it all cubed. There. So now you wouldn't even try to expand. You'll spend too much time trying to expand the 1 plus 4x all cubed and then afterwards multiplying by the 1 minus 3x. You'll definitely back down. Well, I certainly would. So this is a classical case in which you want to use the product rule. Why are we using the product rule? Because it's the product of two functions. Y is equal to u times v. So the u is equal to 2 minus 3x, and therefore the du dx is minus 3. And the v is equal to 1 plus 4x all cubed. Now if you think about this one, we can actually, or we should actually be using the chain rule here. So even within the use of the product rule, part of the differentiation requires the use of the chain rule. And here is clearly a case in which you want to use the chain rule in its shortened form. So the dv dx, chain rule to get your dv dx, will give me, drop the power, 3 times what's in the bracket, 1 plus 4x, subtract 1 from the power, 2, multiply by the derivative of what's inside the brackets. When you differentiate 1 plus 4x, you just get 4. Tidy that up a little bit, and you get dv dx is equal to 12 into 1 plus 4x all squared. The result, dy dx is equal to v times du dx plus u times dv dx. Let's plug them all in. dy dx is equal to v, which is 1 plus 4x all cubed, times du dx, which is negative 3, plus u, 2 minus 3x, times dv dx, which is 12 times 1 plus 4x all squared. Okay, let's see how well I can tidy this up. I can factor out a 1 plus 4x all squared, and I'll also factor out a 3. Let's see. If 1 plus 4x all squared comes out from that, and 3 comes out from that, then the minus is left over from the 3, and a 1 plus 4x is also left over. From the other part, if 1 plus 4x all squared comes out, and 3 comes out from the 12, then 4 is left over from there, and 2 minus 3x. So that's what I have after factorizing. Now, simplify it some more, because inside the brackets, I can open up everything and then rearrange or regroup. dy dx is equal to 3 into 1 plus 4x all squared into. Push that minus inside the first bracket, I'll get minus 1 minus 4x. And multiply the 4 inside the next bracket, I'll get plus 8 minus 12x. dy dx is equal to 3 into 1 plus 4x all squared. Yeah, 1 plus 4x all squared. And on the inside, minus 1 plus 8, that would be positive 7. And minus 4 minus 12 is minus 16x. Voila. I'll leave it just like that. Simplest form. Okay, 2 simple examples. You're going to get plenty more examples to work with. Not to worry. All right. We're going to look at one more rule in this video, and that's the quotient rule. Used, obviously, as the name is suggesting, to differentiate a quotient. There it is. Okay. How do we use this rule? Oh, you gotta learn to write better, write justify and whatnot. Yes, here we go. Give myself a little space. Quotient rule for differentiation. If you have a quotient in the form, if the function y is written in the form of a quotient, oh Jesus. This thing is trying to give me heartburn. In the form y is equal to u upon v, please make sure that the don't mix it up. Don't change them around. The numerator is always u and the denominator is always v. Do not switch them around. Dy dx is equal to v times du dx minus u times dv dx, all divided by v squared. So this one is even a little more complicated than the product rule. There. That's the expression for dy dx. Differentiation does not distribute over division, meaning you don't differentiate the numerator, differentiate the denominator, and then put the two results over each other. That's why you have that rule right there. Right? The distributive law does not work for differentiation when you're dividing. It only works for addition and subtraction. The distributive law, that is. All right, so let's jump into our first example. There. Example number 1. We let u be equal to the numerator 1 minus x squared. And we let v be the denominator, which is 1 plus x squared. Du dx is minus 2x. dv dx is equal to positive 2x. dy dx, I'll write back the quotient rule here. V du dx minus u dv dx all upon v squared. Dy dx is equal to v first, 1 plus 2x times du dx. 1 plus 2x, that's 1 plus x squared, buddy. 1 plus x squared times du dx, which is negative 2x, minus u, 1 minus 2x, times dv dx, which is a positive 2x, all divided by v squared, which is 1 plus x squared, all squared. The denominator squared, v squared. Well, let's tidy up the numerator. We're going to open up all the brackets in the numerator. So dy dx is equal to, I'll multiply the minus 2x into this bracket and the positive 2x into that one. So this becomes minus 2x minus 2x cubed, that looks like. Minus 2x minus 2x cubed. And then 2x by 1 is 2x, but with a minus outside, it's minus 2x. And 2x by minus 2x I'm definitely messing something up here. Let's see this again. V 1 plus x squared times du dx minus 2x minus u, which is 1 minus x squared. Oh, Lord. I'm being, yeah, look, my apologies, I don't know. Maybe I want some sleep. 1 minus x squared, not 1 minus 2x. 1 minus x squared times 2x. Let me double check that again. V is 1 plus x squared. Du dx is minus 2x. And then minus u, 1 minus x squared, times dv dx, 2x, all upon v squared. Open up your brackets there. Minus 2x by 1 is minus 2x. Minus 2x by x squared is minus 2x cubed. 2x by 1 is 2x with a minus in front is minus 2x. 2x by minus x squared is minus 2x cubed with a minus in front is plus 2x cubed. All upon v squared. 1 plus x squared, all squared. dy dx is equal to the minus 2x cubed and the plus 2x cubed will cancel out. What's left on top? Minus 4x. What's on the bottom? 1 plus x squared, all squared. That's dy dx. I'm pretty sure I'm right, but again, please check. I don't know, I'm messing up all my algebra this morning, so y'all please point out if you find any errors. Let me know. All right, let's try another one. Here's another example. Y is equal to, well, I have it there already. The numerator is u. Remember, u is v, the denominator is always v. U is equal to 2 minus 3x, all squared. And v is equal to 5 plus 2x. To get du dx, I will need to use the chain rule. That would be drop the power, 2 into 2 minus 3x. Subtract 1 from the power to the power 1 times the derivative of inside the brackets. And that would be minus 3. If you tidy that up, du dx is equal to minus 6 into 2 minus 3x. I'll leave it like that for now. Oops, I got v squeezed up in the corner there. V is equal to 5 plus 2x. dv dx is just 2. And now I have to plug all that stuff into dy dx, which is v times du dx minus u times dv dx all over v squared. Let's plug and chug. dy dx is equal to v, 5 plus 2x, times the derivative of the numerator, which is minus 6 into 2 minus 3x, and then minus u, which is 2 minus 3x all squared, times the derivative of the denominator, which is 2. U times dv dx, differential of the denominator is 2. All upon v squared, which is 5 plus 2x all squared, like so. Okay, how can I simplify that? Well, usually the first thing I look for is there anything I can factor out to make this, the simplification of my numerator simpler. And there is. I can factor out a 2, and I can also factor out a 2 minus 3x. If I factor those out, if I factor out a 2 from the minus 6, I have minus 3 left. The 2 minus 3x came out, so only 5 plus 2x is left there. Minus, I factored out a 2, and I factored out a 2 minus 3x, I only have a 2 minus 3x left there. All upon 5 plus 2x, all squared. Yes. All right, simplify. Dy dx is equal to, okay, I have my 2 and I have my 2 minus 3x already on the outside. Open up the inside brackets. Minus 15 minus 10x. And then minus 2 plus 6x. I think I got my signs right there. Let me double check. Minus 15 minus 6x. Ooh. Lord have mercy. Minus 50 minus 3 by 2 is minus 6, buddy. Minus 15 minus 3 by 2 is minus 6x. And then minus 2 plus 3x. Man. You know, I'm going to check these... I want to check these outside of these videos, because I'm not sure why my algebra has gone to the dogs this morning. Up on 5 plus 2x all squared. I'll double check that one more time. Minus 3 by 5 is minus 15. Minus 3 by 2x is minus 6x. And then minus 2 and plus 3x. Okay, finally, dy dx is equal to 2 into 2 minus 3x into, I have a minus 6x and plus 3x, that gives me minus 3x. And I have minus 50 minus 2, that's minus 17. All upon 5 plus 2x all squared. Yeah, the only thing you can possibly do there is factor out a minus from the last bracket in the numerator. I'll do that. Let me do that. Dy dx is equal to minus 2 into 2 minus 3x into 3x plus 17. Double check that again. Minus 2 minus 3x, 3x plus 17, upon 5 plus 2x all squared. Yeah, that brings me to the end of this problem. Again, I'll double check these problems myself. I'll just take a break and then come back and check them over, because I'm actually surprised as to how many times I went back and found errors in my algebra. But y'all can check them too. All right, I'm gonna bring this video to an end. And then the other videos are going to deal with differentiating trig functions, and then combinations of trig functions with polynomial functions, and then your chain rule applications, the same chain rule, what I refer to as connected rates of change. I refer to it when we're doing the long form of the chain rule. All right, that's it for this video, and well, I'm out.